So thank you very much, Professor Simon. I see here that you are still an emeritus professor of logic and computation at Kent University, right?
Yeah, that's right. Yes.
You still work part-time there, and also you are a professor of computer science at, I will not be able to pronounce the name correctly, but
yeah, Eötvös Loránd University in Budapest. Yeah,
Budapest, Hungary. And you are also a director of the Marlowe Language CIC, the open source organization supporting Marlowe.
Sure. Yeah,
I didn't know that, and of course you are part of the Erlang Ecosystem Foundation. That's where we met. You were an advisor to Rafael Dueiro Lins.
I was indeed. A long time ago.
Yes, your first PhD student, right?
Yeah, definitely.
And one interesting fact, I don't know if you know him, but there is a Brazilian PhD student there at University of Kent, Paulo Torrens. He works also with functional programming. He was invited by me. He gave a talk last year here on. Let me read the name here. It was compiling with continuations. I'm not sure if he has already finished his PhD, but he had a paper accepted at last year's ICFP. So I really don't know. But thank you very much. You can share your slides and start your talk.
Okay. Well, thank you very much for the invitation. It's a pleasure. I was talking to some friends this morning and saying the only sad thing about this was that you didn't send me an air ticket to get me to fly to Brazil, but it's a good second best to be talking to you and colleagues in Brazil. So thanks very much for the invitation. So what I'm going to talk about is language processing in Haskell, and here's a link that will take you to it'll take you to the slides, but also to the code I'm going to talk about. So I'll just give you a second if you want to. I should have put a QR code there. I'm sorry, but it's not so difficult to read that. And as we said at the beginning, if you have a question, the way I've got this set up, if you just gently interrupt, that's fine. The way I'm doing this, I'm seeing the presentation on my whole screen, so I'm not really seeing anybody else. So if you just interrupt, just say something, and I will be happy to answer a question. Okay. So let me introduce what I was saying. What I'm trying to do in this lecture is not so much introduce new concepts, though if they are new, I hope they're done in a way that you will grasp them. The idea is more to put some simple functional programming ideas into practice in a bigger example. So I'm going to assume you know a little bit about data types, but you will see, as I say, you will see some examples of those. The Haskell read, evaluate, print loop, so that you type something into GHCI, it gets evaluated and printed. That you've got some familiarity with using pattern matching and recursion, and you've got familiarity with writing functions on lists. And what you will learn, from this is, first of all, using data types to represent structured data, and I'll try and motivate that in the next few slides. I want to show that you can process this structured data in a variety of different ways. And in particular, there are a variety of different recursions you might do over some recursive data. There's not just one way of doing recursion. There are a number of ways, of all of which make sense for doing recursion, and building up a suite of functions that compute a number of different things over a data type. So building up an API, if you like. And what I'll also be giving you, it's the case study is very open-ended. So there's plenty of ways that you can think of extending what I'm talking about. So if you get interested in doing something, taking it further, then there are plenty of examples of things you can do, and I'll talk about those at the end. So the topic of this is language processing, and you know, you could say people 10 years ago, 15 years ago in computing departments were saying, oh, we don't teach compilers any longer. You know, nobody ever has to write a compiler, which is probably true. Though I think what's happening now is that people are beginning to teach compilers rather more than they used to, because they're such a good example of how programming is used. But also, you may not write a compiler for a fully fledged language, but in all sorts of areas, you come across little languages that you have to deal with in some way or another. It's something like XML or SOAP or REST or HTML. All these languages require data to be structured in a particular way and for you to process that. Maybe going from a textual representation to a structured representation, or vice versa. But you also find in areas like text processing, something like LaTeX, in system building and making, all sorts of languages are there, which people have invented for configuring and doing DevOps in general, and data analytics. And then the whole area of domain specific languages, that's one approach to solving problems in a particular problem space, designing a language that allows you to talk about the problems that you're trying to solve. So even though you may never write a compiler, you will, I'm sure, spend time writing, dealing with languages in one way or another. So I hope that motivates this example. So the example I'm going to take, it's a simple example. It's numerical expressions like 2 + 3 × 4 or 2 + 3 × v, where v is a variable. So that's the sort of little language I'm going to use. And it's one that I think we're all familiar with, so I don't have to spend a lot of time explaining what the domain is and what the language is, but we can get right into writing programs that deal with expressions. So one question that it's worth asking is, what can we do with expressions? So one thing that you can do with an expression, something like 2 + 3 × 4, is you can evaluate it. It has a value. It's there to describe a computation, and 2 + 3 × 4 has a value 14. 2 + 3 × v doesn't immediately have a value, but if you know that v has a value, then if it has value -2, for example, then 2 + 3 × v has a value -4. So one thing you can do with an expression is you can evaluate it, but you can do other things with expressions as well. One thing you can do without doing any evaluation is you can simplify an expression. So you can turn, what evaluation did was turn an expression into a number. What simplification does is turn an expression into a simpler expression. So you can see the types of these things are different. Evaluation gave us a number. This gives us just a simpler expression. So this is a contrived example, but we'll see later on. It's not entirely straightforward how you do simplification. But in this example, what we can see is that 0 + 1 × v, well, the 1 × v simplifies to v, and the 0 + v simplifies to v again. So that whole thing simplifies just to the variable v. And these are things that we learned at school. You know, we learned to manipulate algebra, and also we learned to do arithmetic. So they're things that we're familiar with, but perhaps we've not programmed them as such. Another thing you can do with an expression, a different thing again, is you can convert it into a sequence of instructions for a machine. So what I've done here is I've taken the expression 2 + 3 × v, and I've compiled it into a sequence of instructions. And when that virtual machine executes those instructions, we will get, hopefully, the result of doing that evaluation, but in a different way. So we can evaluate expressions to get a number, we can simplify them to get another expression, we can compile them to get a sequence of instructions. which separately get evaluated or get run on a machine. So those are three of the things we can do. And as we talk about the representation, I'll talk about a couple more things we can do, which again complement what's going on here. But at the moment, we've seen once you've got an expression, you can get a number out of it, you can simplify it, you can compile it. Now, how do we represent structured data? That's kind of the crucial question in this discussion. How do you represent numerical expressions? Expressions like open parenthesis 2 plus open parenthesis 3 times 4, close parenthesis, close parenthesis. Well, one option is to represent them as a string. So we could say 2 plus 3 times 4, it's just the string, open parenthesis 2 plus open parenthesis 3 times 4, close paren, close paren. Why is that a bad idea? Can I ask, does anyone like to volunteer why representing it like that is a bad idea?
No answers.
Yeah, if you've any answers.
I think the list is too simple to represent all the connections between the elements.
I think yeah. So I think what you were saying is the issue here is all you've got here. There is no structure in that list, in that string. It's simply one character after another. But when we look at that expression, we don't see it as a sequence of characters. We see it as a structure. We can't not see it as an addition of 2 and 3 times 4. And we can't not see the 3 times 4 as a multiplication of 3 and 4. So when we see an expression like that, we immediately read the structure, just like when we see a sentence of English or Portuguese, we see that it's structured. It's not simply so we see the deeper structure behind the sequence of words or characters or whatever. So what we need to do is define a structure, define a type that will allow us to represent that structure. And so what we want to do is somehow uncover a structure like this. So at the top level, we've got an addition, and underneath that, we've got the two arguments, the two sub-expressions. On the left, we've got a number. On the right, we've got another expression, which is a multiplication. And below that, we have the two numbers 3 and 4. So here's the way that we represent this in a Haskell program. We say at the top level, this is a constructor add applied to two sub-expressions, namely num2, the number 2 on the left, and on the right, the multiplication of the number 3 and the number 4. So I've just color-coded the tree again so that you can see the operator top corresponds to the outermost constructor, and then that constructor is applied to two arguments, the sub-expression on the left, which is the number 2, the sub-expression on the right, and that's built with a multiplication. And then you see that it has some numbers below as its two sub-expressions. So that's the structure we see when we see that expression written down. So the way this turns into a Haskell definition is like this. We say we've got a data type of expressions of which there are four different kinds. The first is a number that contains an integer. The second is a variable which contains a character. The third is an addition which contains two sub-expressions, and the fourth is a multiplication that contains two sub-expressions. And I'm saying here, and please give me automated definitions of equality for expressions and ordering. I'm not sure I need an ordering, and a way of printing those out, which will print them out pretty much as they appear in this definition. So if you print out an add expression that will begin with add, and then it will print out the two sub-expressions. So that's our representation. So we're using a Haskell data type to represent those structures. And just as in describing an expression, I say an add has two sub-expressions. So I'm saying I'm using self-reference, I'm using recursion in defining the defining what an expression is informally. That's mirrored by the explicit recursion in this definition. So we say an expression is, one variety of an expression is an addition with two sub-expressions as components. Okay, everyone happy so far? Any questions anyone would like to ask? Any observations?
Oh, no questions.
Okay, I'll carry on. So now we've got a type. There are two other things we can do with expressions. One is we can convert from a string. So we talked about strings as a potential way of describing expressions. We can go from that string, open parenthesis 2 plus 3 times 4, to this structure. And that's called parsing. That's the thing that uncovers, it takes something unstructured and delivers us a structured representation. So that's, you can probably guess that's perhaps harder work to do than going in the other direction, which is taking a structure and turning it into a string. Now, I could have, oh no, let's talk about that later on. But anyway, so now we've just recapping the sorts of things we can do with expressions. We can convert to and from strings. We can evaluate expressions. We can simplify expressions. We can compile expressions. And what I want to do in the rest of this talk is to explain how each of those things is delivered, the different kinds of recursion it gives, the different kinds of pattern matching we might use, for example. So it's an exercise in seeing how out of one type we can get a number of different interesting examples, I think. Okay, so as an example, just to motivate recursion, and I'm sure you are familiar with that, but let me just go through it one more time. Let's say we want to convert an expression like this add applied to num2 and mul num3 num4. We want to convert that to the string parentheses 2 plus, etc. You can think of doing this. Here's a representation of the structure. We can think of building it up as a string in two ways. We can say, well, we know how to turn each of the integers at the leaves into strings. And then once we know, for example, for the multiplication, how to represent the thing on the left and the thing on the right, then we can represent that whole sub-expression by saying it's open parenthesis 3 times 4 close parenthesis. And then with those two representations, we can print the whole thing, because we open a parenthesis, put the value for 2, put the plus, and then put the representation of the whole sub-expression below and close off with a parenthesis. So one way of thinking of that is to build up the answer bottom up. But I suppose the recursive way of doing this is not to build it bottom up, but to build it top down. So what we think of here is, well, how do we print out an expression that is a plus? Well, the answer is it will look something like this. It will begin with a open parenthesis, then we'll have something that represents the left sub-expression, then we'll have a plus, then we'll have something that represents the right sub-expression, and then we'll close with a closing parenthesis. So if somebody was to give me the representation, the string for each side, if I knew how to represent each half, I could then build the answer at the top. So this is, if you like, this is the way that recursion works. We say we can see how to get from the top level if we're given the answers for the two subcomponents below. We've got an add expression. As long as we know how to print the two sub-expressions, then we can print the whole thing. And we can turn that insight into a function that turns an expression into a string. And it says, how do we print out a num n? Remember, that's an expression for the number n. The answer is we'll just show that. We'll use the built-in Haskell that turns an integer into a string. Variables are characters in Haskell and strings are lists of characters. So to print the variable v, we simply have to put that variable v into a list. That turns it into a 1-character string. And then to print an addition, we do exactly what I said earlier on. We have a left parenthesis, we print the first sub-expression, we have a plus, we print the second sub-expression, and we have a right parenthesis, and we concatenate all those things together using plus plus to join the strings. And the pattern of this recursion exactly mirrors the pattern of the recursion in the definition of expressions. So we've got, this is primitive recursion over expressions, where the recursion models the structure of the expression exactly. We had an add has two sub-expressions, and we call the function on those two sub-expressions as part of the definition. And it's no surprise how you print out a multiplication. So that gives us the simplest possible sort of recursion over expressions. Right. Everyone happy so far?
I think so.
Great. Okay. So let's talk about evaluation. And I've talked about this. We can evaluate an expression directly, or we can think about compiling it to a sequence of instructions and then execute that sequence of instructions. And we would expect, whether we evaluate it directly or we do the compile and execute, we'd expect that we get the same answer, namely 14. In fact, you can see there's a slight typo on that slide, but never mind. Right, how do we evaluate an expression? Well, let's write the definition like this. We say if this evaluation function takes an expression and returns an integer. So the base case is if we have an expression representing a number, then the value of that is the number in the expression. So when we had 2 and 3 and 4, each of those evaluates themselves. What about when we have an addition expression? So this is something with a plus at the top. What's its value? We get its value by evaluating the left-hand side and evaluating the right-hand side and adding them together. So what we're doing here is sort of turning the structure, the add in the structure, into a real addition. And so that's, again, this models the pattern of the recursive definition of the data type. And again, similarly for multiplication, we get the same. If you multiply E1 and E2, then you will expect to evaluate E1, evaluate E2, those both give an integer, and then we multiply those two integers together. That's fine. And we can animate the calculation that each of these expressions evaluates the corresponding integer, and then we can multiply 3 and 4 to get 12 and add 2 and 12 to get 14. But what about this expression? What about an expression that has a value in it? Well, here we have a problem, because we can't evaluate an expression with variables in it until we know how to interpret the variables. So how are we going to modify what we've done in order to evaluate expressions with variables? And the answer is, what we have to do is pass in another parameter called an environment, and that environment contains values for the variables. So we can redefine our function like this. So every call of eval, I've added an env argument. And if you look at in the case of num_n, we don't need the environment because the number just evaluates to itself. In the case of addition, we evaluate the sub-expressions E1 and E2 with that same environment, and similarly with multiplication. So all we've done on the first and third and fourth lines is add this extra parameter. But the second line is where we have done something different. And what we've done there is we've said we'll apply this function lookup to the variable v and the environment. And the purpose of that lookup function is to find the value that v has in that environment. Now, I've talked about this without defining what env is, or indeed defining what the lookup function is, but that in a sense doesn't matter. You can see the pattern of what's going on here. We don't have to know the representation of the environment. All we need to know is that there's however it's represented, there is a lookup function that does its job. Now, that being said, let me give you a particular representation here. We can think of the environment as being a list of pairs. Sometimes people call that an association list. So each pair contains a character and an integer, so that the example env1 there associates the value 12 with the variable a and the value -11 with the variable b. And here I've defined a lookup function for that sort of environment. And if you look at the second clause first, and it's one place where you get used to this with Haskell, but if you're not used to, if you were writing this, for example, in OCaml, you'd have to write a rather more cumbersome description of what this second clause does. But because it's Haskell, I can write a complex pattern there. So what I'm saying here is, if you look up v in an environment whose first pair is x, n, and whose its head is x, n, the first thing in the list, and the remainder of the list is p's, for pairs, if you like, then if x, the variable in the first pair, is equal to v, the variable we're looking for, then the answer is n. Otherwise, we've got to look for v in the rest of the list. So we're looking from the left. So the leftmost occurrence of that variable will be the one whose value we will use. And then I've made the decision that if a variable isn't defined, I return the answer 0. I could return an error, but I decided, well, let's just assume that all variables are initialized to 0. Why not? It's a reasonable decision. So that's what my lookup function does. But you can imagine there are plenty of different ways you could represent. You could use maps, you could use some sort of tree representation. But whatever you do, you'll need something, a lookup function that will tell you what the value associated with a particular character is in this given environment. And then we get the case for the variable there. So that gives us evaluation of expressions with variables. And we just had to thread that extra argument through. Okay, so that gives us evaluation. Again, pretty straightforward. And again, this follows the pattern of the definition of expressions, that the clause for addition has two subcalls to the same function on the sub-expressions E1 and E2. But what about compiling and running on a virtual machine? That's a rather different That's a rather different proposal. I have to say what the virtual machine is. I have to say how it runs. I have to say how it what compilation is. So I'll talk about those things now. So it's a stack virtual machine. It doesn't have registers. I mean, it could if we want to, but it doesn't. So what's the instruction push n, where n is a number, pushes that number onto the stack. So if the stack before executing the instruction had 3 and 7 in it, then afterwards it has 3, 7, and 8. So 8 is at the top of the stack. So we have this instruction, the push instruction. We also have a fetch instruction that will get the value of a variable from an environment, because we need to keep the values of variables somewhere. We'll keep them in an environment just as we did before. So if we call fetch A here, that puts the number 4 on top of the stack. And if we call add sub 2, it's saying add sub 2 because it's a 2-argument function that takes the top 2 values from the stack and replaces them by their sum. So it removes 8 and 7 and replaces and puts 15 on the stack instead. And you can guess what's coming next. It's mul2, which takes the top 2 things from the stack and replaces them by their product. So we've got this four instruction machine. Push a number, fetch a value of a variable, and do an addition or do a multiplication. So there's our machine, described informally. But we're going to try and put all this into Haskell. So we need to think, how are we going to work with this? Oh, let me just show you. Let me show you an example. So this expression 2 plus 3 times a, I assert, compiles into this sequence: push 2, push 3, fetch a, mul2, add. So let's see what happens with that. We push 2, so we get 2 on the stack. Then we push 3 and get 3 on the top. And then we fetch a that puts 4 on top. And then we perform a multiplication operation, which takes the top 2 and replaces them by their product. And then we perform an addition, which takes the top 2 and replaces them by their sum. So we've executed this on the stack, and we've now got a stack whose only element is the value 14. In fact, if there'd been some other things on the stack, that wouldn't have affected this. But executing this sequence of instructions has put 1 extra value on the stack, which is the evaluation of this expression. It's a result of that evaluation. So there's our stack virtual machine. So we need to, if we're going to do this in Haskell, we need to decide a few things. How do we model machine instructions? How do we model the machine running? And how do we compile an expression into a sequence of instructions? We'll have to think about those 3, solve those 3 problems. Well, I guess the most straightforward is how we think of modeling instructions. We're going to have a data type, which has 4 constructors. Push takes an integer, and that pushes an integer. Fetch takes a character, and that fetches the value of a character. And we've got add2 and mul2, which request an addition or multiplication. And then we need to think about how to represent a program. We've seen a program is a sequence of instructions. So let's represent a program as a list of instructions. And we've also seen a stack builds up and builds down. It's a linear structure. So we can represent a stack as a list of integers. So we're using lists. They are a very, very common data type. They're a very useful data type. You can model all sorts of things with lists. You can model collections and so on. But here we're modeling, in both cases, we're modeling sequences of things. It's important the order in which the instructions of a program occur. It's important the order in which the values on a stack are represented. So just by designing the types, we've narrowed in on what we want to do with the with our representation. We know how instructions are represented. We know what a program looks like. and we know what a stack looks like. So we should be able to describe how to compile expressions and run programs. So our compiling function will be a function that takes an expression and gives us a program. That is a list of instructions. Fine. What about running a program? Well, that was something that will take a program and an environment, and it will give us an integer, which is namely the integer that's on the top of the stack at the end of execution. But actually that's not going to be enough to allow us to define running a program recursively. We're going to have to add an extra argument. We're going to have to add an argument which is the stack at the current time. Because if we want to, once we start thinking about the states that the virtual machine goes through, we'll be thinking about running a program from a point where the stack has elements in it. So we need to take account of that in the type of the run function. So our run function will take a program and an environment and the current state of the stack, and it will return an integer, which is the result of running that program in the with the stack as it is. So let's see how that definition turns out. This is what we're trying to define. Our function takes a program, an environment, a stack, and it returns an integer. What's the first case? Well, the first case, we're going to do a recursion over the program. We're going to look at, first of all, we're going to look at programs that still have instructions in them. And we're going to potentially do some other pattern matching. But in this first case, the pattern I'm using matching the program is I'm saying the first instruction is a push followed by the continuation. That is the rest of the program. So if we have a push with a continuation, we have an environment and we have a stack. What's the effect of running that? Well, we still have to run the rest of the program. So we have to run the continuation in the same environment, but with the number n pushed onto the top of the stack. So this form of recursion is called a tail recursion, because what we're doing, the answer to our recursive call is to call the same function again at the top level. I'll say a tiny bit more about tail recursion once I've finished this definition. So running a push followed by continuation says, well, what you then need to do is run the continuation in the updated stack where you've pushed the n to the top. And that's what push does. Now, what about fetch? You can see that fetch behaves in a similar way. What we have to do is fetch the value, which we get by looking up. We put that on the stack, and then we run the continuation in that different stack. So this is what we said here. Run the rest of the program in the updated stack. Okay, so those are the two, the push and the fetch. What about this case? The top instruction, the first instruction is add 2, followed by the rest of the program. Now, add 2 requires that there are at least 2 integers in the stack. It says take the top two off the stack, add them together and push them back on, and then run the rest of the program. And that's what we're doing here. We're running the continuation, same, the environment never changes, and we now, instead of having n1 on top of n2 on top of the rest of the stack, we have n1 plus n2 on the rest of the stack. So the stack is 1 element shorter, and we've added the top 2. And as ever, you can imagine what we do with multiplication. We do take the top 2 and multiply them. Now you can see here, I'm doing a more complicated kind of pattern match here. I'm assuming the program, which is a list. I've done a case analysis over a non-empty program, the 4 different cases. But in the case of addition or multiplication, I'm only defining this when there are enough elements on the stack. And then finally, the last case is when there are no instructions left. And what I'm putting in that case is I'm saying when there are no instructions left, when the program is empty, and we have n is the top element on the stack, I return that value. And that gives me, that is the full program for running the stack machine. In fact, what I'm doing here is I'm saying I don't care if there's anything more on the stack, I'm just returning the top element. I'm not forcing it to have an empty stack. I could do that and force an error there. So there will be some cases that are not matched by this definition. If I ever meet to add an instruction when there aren't at least 2 elements on the stack, I will get a pattern matching error. But that's fine. You know, it's an error. And I can, if I have properly compiled the program, if the program I'm running is a result of compiling an expression, as in not a random sequence of instructions, then I can be sure that situation will never arise. So I got this. I talked about tail recursion. You can view tail recursion as an imperative loop. So this is like a loop that runs through the program, updating the program to run the environment and the stack. So you can see when I do a tail recursive call, it's like updating a program environment and stack variable, if you like. That's a way of looking at it. So this recursion is very unlike. This is not, it's structural over the length of the program, but it's also requiring some extra conditions over the structure of the stack. So, and it's tail recursive rather than directly recursive. Okay. So there we've got our stack machine and we've got a program that can run. We know how to run a program. How do we compile? Well, this is perhaps clear from what I've been explaining so far. To compile a number n, we simply push that number onto the stack. To compile a variable, we fetch we put a fetch on the stack. So the number n has a 1 instruction program, push n. The variable has a 1 instruction program, fetch v. What about addition? Well, what we expect the compiler to do is what we expect the machine to do is if we put a program into that, if we run that, execute that program, then at the end of the program, the value of the expression we compiled should be on top of the stack. So if in compiling addition, we compile E2, and then after executing those instructions, the value of E2 should be on the stack. If we follow that by compiling E1, the value of E1 should be on top of it. So we should, after executing those 2 sequences of instructions, have the value of E1 and the value of E2 in the top 2 cells on the stack. If we follow that by an add 2 instruction, it will remove them and replace them by the sum of those 2 values, which is precisely how you evaluate the add. You take the result of the results of 2 sub-expressions and add them. So you can see here that the effect of those compilations of that sequence of compilation is to precisely put the result of the add as the value left on the top of the stack. And as ever, multiplication follows along behind. So we've got compilation, and then we can test and see whether if we compile a program and then execute it, and run it, we get the same as we get with direct evaluation. And moreover, I'm not going to talk about this in depth, but one of the nice things that we can do with functional programs, it's not an accident that we write these definitions with an equals. It is the case when you write a functional program in Haskell that the thing on the left-hand side of the equals is actually, and always is, equal to the thing on the right, so that we can use these equations as logical equations. And so we can prove that if you compile an expression and then run it, then the value that comes out of the run is precisely the value that you get by directly evaluating the expression. And we can do that by, it won't be a surprise to know, by using induction over the structure of expressions, just as we do recursion. We define things by recursion over the structure of expressions. So we can write proofs that indeed interpretation, if you like, eval, is the same as compilation. So what have we seen? We've seen how flexible data representations are. We've got, we're using lists for various things. We've seen how we can use pattern matching to express definitions at a nice high level, denotational, readable way. We've seen tail recursion, and we've seen the missing cases to let it fail. So that's a sort of Erlang idiom, if you like, that's snuck into Haskell. But let's go on and let's look at parsing quickly. Now, parsing, as I said, parsing is the more difficult of the problems of going to and from strings to expressions. Pretty printing, going from a structure to a flat string is pretty straightforward. It's you just squish it all down. What we have to do in going in reverse is we've got to somehow dig out the structure that there is in the expression and make it manifest, make it explicit. And let's think first of all about the types involved. It's always good to get, when you're thinking in a functional context, if we want to write a parse function, we ought to think what sort of type it should have. So we would expect we'd write a parse function that would do something like this. It would take the string, open parentheses, 2 plus, etc., and return the structure that you see there, add the expression num2 and the multiplication expression. And if we parse the string with just 2 in it, we get num2. Parse the string with just a in it, we get the variable a. Fine. But not quite fine. Because what about if we parse this string, the string with 2 plus open parentheses 3 times 4, what expression can we extract from that string? Well, the answer is the expression at the beginning of the string is just the number 2. But if we return just the number 2, then we've lost the bit that is still as yet unprocessed. So what we need to do instead is to think about our parse function returning a pair. It takes a string and returns an expression and the bit of the string that wasn't used to form the expression. So in the first two cases, first two examples here, the second item of the pair is empty. But in the last case, we said we found the number 2, and what's left over is the string plus open parentheses 3 times 4, etc. So we return this expression and what's left of the input. Now, I've chosen a particularly amenable grammar, particularly amenable form of expressions here, that we might have to do something a bit more sophisticated in general, but this is by way of illustration. And this is good enough for doing what we want to do. And let's look at the algorithm informally. What do we have to do here if we're parsing a string like this? What the algorithm has to do is it has to spot an opening parenthesis, because a complex expression, an expression that's an application of an operator, always begins with an opening parenthesis. And then that is followed by an expression. That expression here is 2. It's followed by the operator, which is plus here. It's followed by another expression, which is 3 times 4. And it's followed by a closing parenthesis. So this is a deterministic algorithm. At every point in doing this, it knows what it's looking for. Opening parenthesis, expression, operator, expression, closing parenthesis. And we can turn that into a Haskell definition. And again, we're using pattern matching and here to express precisely that. So here is our parse function, and it says, we're in the case where we begin with a and left parenthesis. So there'll be other clauses for parse, which I don't talk about how you deal with parse numbers or variables. They're not so interesting, but you can find them in the file. So assuming that we start with an opening parenthesis, what do we do next? The rest of the string is rest. Well, what we do is we parse that. So we apply parse to rest, and we pattern match the result. So we say E1 is the expression it's found, and rest1 is the bit of string that still remains. What do we do with rest1? Well, rest1 has to begin with an operator. So we pattern match operator and rest2. That's the tail, the remainder of that string. What do we do with rest2? We look for another expression at the beginning of it. So we say apply parse, and we expect that to give us E2 and rest3. And then we expect a closing parenthesis. So we pattern match rest3 against the closing parenthesis and rest4. And the result we return is either add E1, E2 if the operator was plus, or mull E1, E2 if it was multiplication, paired up with rest4, because rest4 is what remains. It's the thing that's been unanalyzed in this process. So the recursion here matches the structure that we saw in the string. We have a opening parenthesis, a sub-expression, closing parenthesis, operator, another sub-expression, and closing parenthesis. And those sub-expressions correspond to calls of parse, but they're parse on the remainder of the string. The string keeps getting chopped down. So this is what's called predictive top-down parsing, and it's another recursion pattern over. So it's a recursion pattern over strings that mirrors the recursive definition of expressions, which is not surprising, because what it's doing is it's uncovering that expression structure inside that flat string. So that gives us parsing. As I say, the other side, how you parse the numbers. Parsing variables is straightforward. Parsing numbers is a bit tricky, but you can find that in the file. Right, I talked about this already. How do we make sure our programs do what they're supposed to do? Well, we can write proofs, and this is the proof I was talking about earlier. In fact, we can, for all expressions and all environments, we can say that evaluating expression in that environment is the same as compiling it and running that program on an empty stack. So we do that using, and for example, we can prove other things about the correctness of parsing. We can say, if I have an expression and I print it out using my print function and then parse it back, I'll expect to get the expression and no string left. So we prove these things, and what's nice about that is that we know, if we've written a proof like that, that we're able to be sure that this behaves as it should in all possible cases. Now, there's an argument that says proof is still expensive and difficult and manual. I think that is sort of getting blown away by a combination of two things. One is the rise of SMT solvers, which allow you to do an awful lot of automated proving without having to write any sort of tactics or whatever. And also the rise of AI. I think AI is proving, for relatively straightforward proofs like this, it's becoming easier for AI AI systems to develop proofs or proof scripts, which indeed do prove what they're supposed to. And of course, the nice thing about using AI here, if what you're doing is using the AI to guide a theorem prover, a system which will only produce correct proofs, the AI can never get it wrong. If it produces a nonsensical script, then it just isn't a proof. So there's no danger of AI proving something that isn't valid. So that's a real advantage if you combine the AI with a solid system. Okay.
We have a question by Lucas Paixão.
Yes,
Lucas, do you like to ask, or do you want me to read it? I'm going to read. Maybe he has.
Sure.
He wrote, "Is this already achieving theorem proving by implementing dependent types, or this would be within the next steps?"
I think it's more proving things equationally can be done with dependent types, but you do still have to, something like AGDA, you still have to work quite hard to prove those things. What you do is you develop a functional program that effectively is the evidence that the two sides of the equation are equal, and that's a proof in another form. But I think the point I was trying to make was that developing something like that, or a list of tactics in something like ROC or Lean, you can develop, an AI might be able to develop those things and then check, then the AGDA system or the Lean system can check whether or not the thing the AI has proposed as a proof actually is a proof. So I think it's not a case of an AI having a human in the loop, it's an AI having a theorem prover in the loop that can keep it honest. So dependent, you could choose to use dependent types, but I think you still have to brief some sort of proof. And in fact, doing equational reasoning in dependent types can be a bit tedious. But that's another story. But I hope that answered your question.
He wrote, okay. Thanks.
Thank you. Good. Okay, so let me just say a few things about taking this further. Things that you might, if you wanted to add some things to this grammar. I'll actually talk about simplification in a second, but you can imagine adding things like subtraction, division, and as you add things, you might have to change the types of if you add division, you might worry that if you divide by 0, you need to deal with that. Do you finish up with evaluation returning a maybe int and returning a nothing in the case that you do a division by 0, for example? You could imagine adding variables. You could add let expressions. You could add other types like Boolean types. You could have your own functions. You could change the grammar, change the syntax. So I didn't have to parenthesize everything. That wouldn't make any difference to the expression type, but it would make parsing more difficult. But I just want to conclude with the simplification example. And this is a case where it really is not the case that this is structural. The recursion pattern that you see here is not simply one which where you just apply the function on sub-expressions and get the top level result from that. So for example, look at this. Here's some cases of what you might do by way of simplifying. If you add E1 and 0, well, that's the same as E1. So simplifying that whole thing, you get just by simplifying E1. The same with multiplying by the number 1. And multiplying by 0, that's straightforward. You just simplify to 0. That's the most radical simplification. But what in general do you do? How do you simplify E1 and E2? Well, one answer would be simplify them both. So simplify E1 to S1, simplify E2 to S2, and then return the answer, add S1, S2. That's not good enough. The reason is that as you simplify S1 and S2, you may produce yet another top-level simplification. So, for example, suppose S1 simplifies to 0, then you further want to simplify, add S1, S2 to S2. So here you see quite a complicated recursion. I simplify E1 and E2, and if it's not the case, well, if it is the case that at least something has changed, then I simplify the addition of the simplifications. Otherwise, I just return the addition of the simplifications. If I didn't have this check and I just call simplify again on add S1, S2, willy-nilly, I would go into a loop as soon as normal simplification took place. So that would be silly. So you can see here that the pattern now of the recursion is substantially more complicated than simply doing things on the structure of the expression. As you simplify, then you more simplifications manifest themselves, bubble up to the top, if you like. So it's not simply a top-down algorithm. Things emerge as you simplify. So I think that was the last example I wanted to talk about. So just shows that even with that simple data type, there are different kinds of recursion, use different kinds of recursion over lists, and so on. So I hope it gives you some power, an illustration of the power of different kinds of recursion, different forms of pattern matching, thinking about type-driven development. So thinking before we write our functions, thinking about what type they should be. It sounds obvious, but in some languages that people just don't do that. And thinking, first of all, about the types that we want to use to represent our various kinds of data in the domain. Okay, so I think if you want, I'm in the process of revising this. It's going to be completely freely available online when I get it done. But for the moment, you can get a PDF of this for free from this website. So if you're interested, that's the place to go. And there is a bit about this in the book. And this is where the resources are. If you want to download the code I've been talking about, and any questions? So I'm sorry if I've overrun a tiny bit. Oh, that's not too bad.
No, that's okay. Perfect. I didn't know the book was available for free.
Yeah, okay, yes, tell your friends. It is, yes, yeah. But the plan is to make it, I mean, at the moment, it's just a PDF online. The plan is to make it, a proper online text. And so that's, and it needs revising as well, because that edition dates from 2011. So it doesn't have stuff about applicative and functor and so on. And so there's some small things that need revising. But anyway, yeah, it is there for free. So yes, do download it.
Okay. Any question from the students? I think, Philippe, are you going to ask something?
I might unshare if I can. No.
If you're still sharing, I do have one question about the last thing you were explaining. Maybe I'm not very familiar with Haskell, so the syntax is a bit new to me as well. But I was very curious how you were explaining how when you were doing the expression simplification, as you go, you will be simplifying into something that can also be simplified again. But I really didn't understand how you were solving the problem with recursion in this case, how you were figuring how to stop the recursion.
Let me, where should I, what should I do? Oh, what I could do, if you bear with me a second. Oh, can I do this? Give me a second and I will connect my iPad and then I can scribble some stuff. Would that be, give me 10 seconds. Is that okay?
Yes, of course.
Let me, iPad. Sorry. Yeah, I should have done this in advance. Oh, I don't know what's doing this. It doesn't seem to want to play. Okay, I can't do it. Let me just pull up an edit window. Okay, let me do this. Let me go back to sharing. If I can do that, where am I? It's in Safari, isn't it? Okay, sharing, share screen, share window. Oh no, I don't want to do that. Sorry. Share my screen anyway. Sorry, it's going to go. Here we are. This is what I want to do. Let's blow up the font. Okay. So suppose we have something like this. 0 plus 0. And if you don't mind me doing this in times 1. And I say I want to simplify this. And at top level,
I'm sorry, I think I'm not seeing it. Are you sharing this FP planning or?
Oh, sorry. I know I don't mean to be sharing that. Sorry, I must be sharing the wrong thing. Let me stop sharing and let me do the whole screen. Here we are. Share entire screen. Now, are you seeing something? Top left. Are you seeing it?
Yes.
Yeah. Okay. Sorry about that. Okay. So you could say, I mean, if I write this, it's just to simplify. If I simplify this, I could say, well, okay, what I can do is say, well, that's equal to it's equal to simplify of 0 plus 0 times simplify of 3 times 1. Yeah, that's the and then that indeed those simplified and that becomes simplify of 0 plus 0, which is actually 0, times simplify of 3 times 1, which is 3. So that becomes 0 times 3. But then I stop. What I want to do is I need to say simplify here. That. I want to simplify that result because that then will give us 0. Does that make sense? Without this step, if I remove this step, if I could just stop here and that would give me 0 times 3. But it's not in its simplest possible form. I need to revisit the top level because I've changed one of the things because one of the things here, in fact, both of them here have changed. So I need a new match at the top level is possible because because that 0 plus 0 has simplified to 0, and then now that whole thing simplifies to 0. So what I could say in general is this. I could say simplify of add S1, it's E1, E2, is simplify the add, simplify E1 and simplify E2, and then simplify the whole thing. I could do that, but that is too recursive. That's too powerful because if you think about what happens in the case of simplify add 2, 3. Sorry, the syntax is going to be a bit wild, but that's going to be simplify of guess what? Exactly the same thing.
The same, yeah.
So yeah, sorry, yeah. So what I have to do is I have to guard against that. So what I do is I say it's this. Remove this. Sorry. But just let me say S1 is simplify. Just lift these two definitions out. That's my cursor. Here we are. Lift these two definitions out. So S1 is this, and S2 is this. So just naming those two definitions. Whoa. Naming those two definitions. So that's saying this, but I only want to do this simplify in the case that at least one of S1 doesn't equal E1, or S2 doesn't equal E2. Ugh.
Okay, so in that case, you are actually comparing the simplifications itself.
Precisely,
So so you know when to stop the recursion. Okay,
precisely. So I only call that extra recursion, that extra top level recursion, when at least one of these things is different. So the thing I'm applying simplify to here is not the same as the thing I'm applying it to on the left. Because otherwise, if it is, then I'm just defining a black hole. So you need to, and that's why it's a bit subtle. And you can see that it's going to terminate. There is an argument around the size of the expressions that you're applying it to. So you might think, well, this looks like a top level recursion. Ooh, that's a bit, but the fact that at least one of these, oh, sorry, that's S1 equals E1. That should be E1, sorry. At least one of these is unequal means that it's at least one of them is smaller. So if you look at the size of the expression on which simplify is being applied, then the size of the expression always gets monotonically smaller, so the recursion always terminates. But it's a complicated, it's not a structural argument so much as a sort of it's like a metric. You've got a measure of the size of the expression, and it is your recursions are safe in that measure is going down. But it would be getting something like Agda to accept that might be not entirely straightforward. Its termination checker you'd have to assure it. That's an interesting question, whether you could get Agda to. Yeah, I'm sure you could, actually. It shouldn't be. Okay, but yeah, thank you. Sorry, I glossed over that more quickly than I should have done.
There are other questions here in the chat. One is by
and thank you.
No, pleasure. Let me unshare. There we are. Fine.
By Fabio Kleis. He asks about deriving ORD on expert type definition. Why do you need ORD? I didn't see any ordering.
That's a very good question. I don't know why it's there. It could be, why might you want ordering over expressions? I mean, in the simplification case, you might use it. You could probably, if you defined ordering in the right way, I think you would find in my simplification example that you were calling it on things lower down in the ordering. So that would be, yeah, I would imagine that would be the case. But you're right. Sorry, it's often I simply put it in there as a and I could have omitted show and used my print function as a show function. But it's quite useful having the built-in show shows the thing as the algebraic data types, and my print function shows them as sort of pre-printed as arithmetical expressions. So it's it's giving you two different views of that same representation.
And Fabio wrote, maybe operator precedence. The reason for the ORT was operator precedence.
No, I don't think so. I mean, I'm not using operator precedence. I've avoided that by having everything fully parenthesized. So yeah, I don't think, yeah. No, I think I just put ORD in there. I'm sorry. It's good for you. Thank you for picking me up on that. I should remove it. Yeah. In fact, I did. Did I use the equality? Yes, I did, didn't I? I used equality in the simplification. And that's full equality over expression. So I do need that.
And another question by Lucas Paixão. I was wondering about the simplification tool and assumed it had something to do with induction and maybe algebraic data types, since these are also implemented using pattern matching.
I think I think you're reading too much into it. I think it was just a mistake. I put it in there. It was in there as a it didn't do any harm, but I didn't use it. I think that was the. So Felipe, I'm seeing your question about Elixir. That's it. I don't know. I mean, things are very fluid. I mean, Elixir is getting lots of take up in small companies. Certainly in the Erlang world, startups are using Elixir, not Erlang. I think Erlang. It seems to be that people have migrated. People like WhatsApp are still using Erlang. I mean, that's still, so there are big users of Erlang out there, but certainly in terms of startups, people are using Elixir, or some people are using Gleam. I mean, it's quite a risk to use a language that's recently been invented. Elixir has been around quite a long time now, isn't it? Is it about 10 years?
More than that.
More than that,
years.
yeah. I mean, Haskell has been around 30 years, more. I mean, languages take a long time to get adoption. Haskell is perhaps 35 years. I mean, people use Haskell. People use there's F# in .NET that gets used in quite a lot of financial institutions. Use that because they can link it with spreadsheets that they write in Excel and so on. F# is newer. But F# is really OCaml. So in a sense, F# is old. F# is yeah. Haskell, yeah. But AI generated Haskell programs. Would you recommend the use of a Haskell copilot? I mean, I don't see why not. That if it's a copilot. So I think my feeling about AI, and this, we could talk about this forever, but my feeling about AI is it's fine if there's a human in the loop. If you are in the driving seat, then, and if it is a copilot, and that's what copilot means, that's fine. It's just I don't want AI flying the plane. It's not with that analogy. And so it's good, but it's not always right. I mean, AI is just statistical generation, even though it looks magic. So there's lots of answers to this question. I mean, one is that at least up to very recently, I think AI wasn't terribly good at helping with automatically solving things that were issues in real GitHub repositories, because those are messy, because they're to do, it's a big project typically, or it's a project that is, might use different libraries and so on and so forth. So all the messy stuff to do with builds and to do with different platforms and to do with different libraries and versions of libraries and all that stuff, AI isn't terribly good at. It can solve the exercises in my book pretty well, maybe because it's been trained on those, but also because they're fairly straightforward. There aren't many different solutions to write a 10-line program to do this, and so it can do that. So I did some work with some people who were using Haskell a lot. This company IOG, who were using Haskell in a blockchain context, and I know that people there were finding using something like Copilot as a way of doing code reviews was helpful. So saying to, and in a sense, that's using AI at what it's good at. It's saying, take this thing and summarize it, rather than invent me this new thing, like write a program. It's saying, tell me what this program that's here, this concrete, what this program can do. So using it in that context, I think is, it's not without potential risk, because it might misinterpret, it might miss a side case and so on, but it's more, but I think that's a safer use. So, I think it's just going to be there. It's just one of those things that I wouldn't say don't use it. But of course, one of the problems, Adolfo may say precisely that. One of the problems is, of course, if AI solves all your problems for you, you never learn anything. So there's a pedagogical issue. And this is something that's coming in, and I don't know how this will turn out, because, arguably what's happening with AI is that people are taking out the lowest. There's a hierarchy in software engineering. You have junior engineers and interns and so on. And what you can potentially do, I'm not sure you can in practice, is say, well, we don't need the lowest layer any longer. We don't need new graduates, because we can get AI to do what they would do, and then it's reviewed by people who are more experienced and so on. But then, if you do that, how is anybody ever going to get experience ever again? How are people going to learn if they have not for themselves solved those problems from which you learn? Computers can do arithmetic for us, but that doesn't stop us learning how to do arithmetic at school. And I think in a similar way, that is a conundrum. But I see, if you follow the financial press, there's so much hype about AI, and so little evidence that all the money is being spent. Well, yeah, I think, Raphael, yes, that's a good point. Yeah, so there's an interesting example of this. If you look at Stack Exchange, since the rise of AI, there is the number of questions on Stack Exchange has gone down quite substantially. And because all the stuff that was in Stack Exchange is now inside AI, but it's not renewing, because people aren't asking new questions inside Stack Exchange. And so the quality, I suspect, of responses to people's questions is going to go down, because there's no new input. So I think there's all sorts of problems with it. Yeah.
Yes, you mentioned Lean during your, I believe, the last few slides, or was after the question. But I know
Yes.
the creator of the Lean programming language, Lean Prover, he's from Brazil too. It's Leonardo de Moura.
Yeah.
And I follow him on LinkedIn, and almost every day he's reposting something. Oh, this new company here got $100 million. I don't know the amount exactly, but
Yes.
To use AI with Lean. So it's
Yes.
kind of, they are working a lot on that. I don't
They
know
are.
if it's,
And I
they are
think
going to get results, but
and I think if what I think this is right. I mean, I was saying it. I haven't checked it for Ling, but I'm sure if it's structured like other theorem provers, and I'm sure it is, then there is a core which, in the end, that's the core which checks whether or not something is a theorem, and that is the AI might generate something that's fed to the core, but the AI is not in the core, and so there is no, as far as I can see, there is no danger of AI contaminating what something like Lean is doing. I mean, what it might do is it might de-skill people. It might mean there's less you can see there might be sort of second order bad effects, but at least it's not going to, I hate this phrase, it's not going to hallucinate proofs, because they're not, it's not a proof until it's a proof. And that's good. And certainly if you feed it, if you feed it exercise questions from a computer science course, say, AIs will give you something that looks like a solution, but it's not always the case it is a solution. It's something that looks like a solution, but it could be, there are situations where it will not be a solution. So it's not foolproof. And of course, the irony with that is the only way you know it's a solution is to have solved the problem yourself. So it's not helping in that respect. Yeah.
Yeah, the code may be completely wrong, actually.
Well, the code may be wrong. Yeah, it may be wrong, but it may be incomplete. I mean, the code being wrong is okay. Well, it could be wrong semantically. It's not going to be wrong in terms of syntax, because then it'll be rejected by your VS Code or whatever. But the code may be subtly wrong. It may not do simplification right. It may not be. It may. Yeah.
Yeah, we were about to finish an assessment of the quality of code generated by several AIs, and I was surprised, really surprised, because actually the original assessment was about performance. We were concerned, how good is the performance of AI generated code? But we were really surprised with the number of programs that did not compile, the number of programs that compiled and produced wrong answers, and the number of programs that compiled, executed, and the answer was not completely right. And the performance was dreadful.
And that's the danger. It's the ones that are almost right, isn't it, that are the danger. Yeah, because in a sense, the ones that don't compile, you can throw out
immediately.
But it's the ones that look and feel like they're doing the right thing. That's the tricky thing. Yeah.
Yeah, one of them was a classical problem that we asked to generate pi with 1,000 decimal bits. And what it did was that it generated pi with correctly up to 200 digital digits, and then after 200 it went berserk. So it is something that really worried us.
Yes. I mean, could you look at the program and see why it went berserk?
Yeah, well, that would be quite hard.
Oh yeah, sure, yes, yeah, because that's the problem.
Anyway.
It may not produce readable code. Again, that's a
Well,
okay.
thank you very much for your beautiful talk.
Well, it was really nice to see you. Thank you for coming, and thanks everybody else for coming. It's been. Thanks for the questions, because it's really nice not to be speaking to myself all evening. It's been good. So thank you for being here. Yeah.
Thank you very much.
Okay. And as I say, next time, send me an air ticket and I'll come.
Okay. Okay, if possible, I will.
No, I'm joking. I know, but I did think, oh, it'd be nice to be, yes, as it's getting cold and wintry here, even more so. Yeah. Okay. So thank you very much. So I leave
Thank
now.
you.
Okay. Bye-bye.
Okay.
Bye.
Bye-bye.
Bye, Raphael. Bye.